Hello, in this video I'm going to take a look at force diagrams, so how to draw them and why they're useful. So I'm just going to sort of sketch up a few standard situations that we tend to encounter in classical mechanics problems. So I'll start with an object on a slope. So we've got some slope here which is at an angle theta to the horizontal. We've got our object sitting on the slope. We'll make the slope rough, so the object sitting there may be in equilibrium. I mean, who knows? But we got friction in play. So we're going through the same steps when we're drawing force diagrams. So we just need to go through each one of the forces that we consider. And there aren't that many of them. We got gravity, normal reaction force, tension, friction, and that's about it really. Unless they happen to have put in air resistance as well, but we don't tend to have that. I mean, they might have given us something to do with a general resistance to motion. But really, we're just drawing on the arrows for those four forces. So the first thing we need to decide is, well, what objects are we interested in? In this case, we're looking at the motion of the object that's on the slope. We don't care about the slope because all our forces are in pairs. Do we need to draw all of the pairs of forces? The answer is no, we don't. We want to draw the forces for the object that we're going to analyze. So in that case, in this particular case, it's just the object that's on the slope. So we just need to draw on each one according to the rules of that force. So we start with force due to gravity, the weight. So we go from the center of mass of the object. So I've drawn a dot in the middle, assuming this is a uniform object. Arrow directly down, and we will call that the weight. We can then put on our normal reaction force. So we've got a plane of contact here between the object and the slope. So at 90 degrees to that, okay, slightly wonky line, but that's just me drawing this freehand. So perpendicular to the slope, we've got our reaction force. So that has to be perpendicular. Then we want to put on, well, we haven't got any tension. There's no ropes or anything, or strings or tow bars or anything, so we don't have to worry about tension. Then we've got friction. So we can draw friction. Some people draw it along the surface because it is at the surface. So that's where I'm going to put it. I mean, it doesn't matter too much if you draw it out of another part of the object to make it a little bit clearer. And then I'll put friction up there. So we've marked on all of those. We can say also something about the angle that the weight is acting at compared to the normal force, because that is going to be the angle of the slope. And we're also going to want to mark on a potential acceleration as well with our double arrow. So if anything is going to accelerate down the slope, so mark on the double arrow of acceleration with an A. So that's put on everything for this particular diagram, and we're going to see how we're going to be repeating this for other diagrams. We're just doing the same process every time. So say we extended this diagram. We've still got our slope at the same angle to the horizontal. We've still got our object sitting on the slope. But this time, at the top of the slope, we've got a pulley and there's a rope that goes over the pulley and then hangs down. So we've got this sort of wedge slope now to another mass on the other side. So we've now got connected particles. So a lot of this stuff, we're going through the same steps again. We need to start off by saying, well, which objects are we interested in? Well, we've now got two objects here. We've got these two masses. We don't care about every point of contact, but we go through some of those as we go through drawing a diagram. So we start off again with weight. So mark on the weight for this object. So we have to call that weight 1 now because we've got two of them, two objects. And then we can mark on exactly the same from the center of mass of the other one going straight down. So that's our two weights. Now we look for points of contact. We've got our normal reaction once again for the object on the slope. This object that's hanging down, well, is not in contact with anything else, so there's no normal reaction force. We do have a normal reaction force at the pulley, but we're not going to be analysing the pulley, usually for the reason that they will say in the statement of the problem that the pulley is smooth. So they'll say it's a smooth pulley. So we have no other forces there. We've got no friction, we've got no losses going on there, so we don't need to do an analysis of the pulley because there's no energy loss. Yeah, there's nothing happening there that we need to be concerned about, so we don't have to draw in the reaction force that will be happening at the pulley, so we can just ignore that bit. So we've done reaction force, we've done weight, friction. We've still got friction going, well, it doesn't matter which way you draw it on these. I mean, I could have had now friction going in the opposite direction. I mean, maybe this mass is getting dragged up the slope. Doesn't matter. Just draw it on. If it turns out the friction is in the opposite direction, we'll just get a negative answer when we solve everything. So it doesn't matter which direction we put our friction arrow. It does make sense though to have the friction in the opposite direction to the motion, because it has to be, and I don't know, sometimes again it doesn't really matter with the acceleration, you could have it in either direction, but let's have it going against the friction in this case, especially if these objects are starting from rest. Then it makes sense, because if they are starting from rest, then the motion will go in the direction of the acceleration, so the friction must be opposed to it. So let's draw acceleration going down the slope for the mass that's on the slope, which means the acceleration will be upwards for the other mass, and they will both be acceleration A. We haven't got an A1 and an A2 if the string is inextensible. So that's something that we need to consider in the question. We also don't have to mark on the weight of the string if the string is marked down as being light. So this is why they'll be describing this in our question, that we've got a light inextensible string. The only thing we have to do with a string is mark on the other force that we have, which is the tension. So the tension in a string will always act away from the object that it's attached to at the point of contact. So we've got a T going upwards from this mass that's hanging down on one side of the slope, and then we've got a T going up again for the object that's on the slope itself. And these T's will be the same because the string is inextensible. It's light and inextensible. So there's no extra force that's provided by the weight of the string because it doesn't have one. And there's no variability in the tension because it's inextensible. So we've marked on all of this now. We've got all of the forces applying to each of the two objects that we're interested in. So that's all good. Right, let's try let's try another one with something leaning against a wall. We haven't done one of those. So we've got a wall and we've got a floor and we've got a ladder that's leaning against each one of those. So let's put a rough surface on each one of them. Sometimes we draw these sort of lines in. People take these lines to mean different things. There is quite often showing we've got a solid surface there, something that's not going to be moving in any way. It's completely fixed. I mean, we could have drawn that on the slope going on here. Sometimes people use this to denote that it's rough. It's a little ambiguous maybe. but still, we've got a ladder leaning up against this wall here. Let's make both of the surfaces rough. Start with the usual. Let's put the weight on. So center of mass, if they're telling us it's a uniform ladder, we can put the center of mass right in the middle. And then weight going straight down, arrow straight down, weight. Normal reaction force, each point of contact, so perpendicular to the wall. We've got one reaction perpendicular to the floor. We've got another reaction. So again, going through the same process we had for the others. We got no ropes or anything, so there's no tension. And then we've got the friction. So if this ladder was going to move, it would be sliding down the wall and across the floor. So we're going to have friction going upwards here, opposing that motion. So one lot of friction and then another lot of friction, which would be opposing the sliding across the floor. So once again, marked everything on. So once we've drawn these, I mean, these are then really useful because they're giving us a framework for doing our analysis. All of the analysis that we're then going to be doing off of these is applying F equals ma and the friction is mu r. So let's look at case number 1. If we were going to analyse this, we'll be analysing it for the one object that we're interested in, and we're going to set up 3 equations off of this. So we're going to look at the forces perpendicular to the plane. So we'll be doing F equals ma perpendicular to the slope. So if we apply that, we've got r going in one direction. So we'll make that, say, a positive r. In the opposite direction, we've got w cos theta. W cos theta. And that is going to be equal to the mass times the acceleration perpendicular to the plane. So if the mass of this object is m, then we'll have m times 0 because it's not moving, it's not accelerating perpendicular to the plane. So that would be equal to 0. We've got our F equals ma parallel to the slope, which is going to be that w sine theta going down the slope minus f going up the slope is going to be equal to ma, because we do have an acceleration this time. So we can see we've got 2 equations here with 1, 2, 3, 4 unknowns, f, w, r and theta. So we need some more equations. We've got that f is equal to mu r for our friction. So that's one thing that we can build in. Oh, of course, we've got the mass as well, which is another unknown. We've also got that W is equal to mg. The weight is the mass times the acceleration due to gravity. That is our simplified version of Newton's law of gravitation. If you remember what we were saying about Newton's law of gravitation, where we've got F equals g m over r squared. If you replace the capital M over r squared with the mass of the Earth and the radius of the Earth squared, then this is going to reduce down to acceleration due to gravity, including the universal constant as well. So that's giving us our g, the gm over r squared bit. Which allows us to quantify our weight, because this W here in weight is this F that we're calculating. So we just have to compare these two things. W and F are the same, then small g is capital G, capital M divided by r squared. So providing we know something about this setup, like they'll probably give us, say, the angle, the mass, maybe the coefficient of friction, then we can work out everything else off of our simultaneous equations. And this is exactly what we'll be doing in the second case as well, except now we can set up, we can do all of this again for the first object that's on the slope, and then we can do it again for the second one. you know, you can treat these, it's like you're putting a little dotted line around it. You know, this thing here hanging on the string, it doesn't know anything else outside of it. We're just applying these rules to what's inside that little dotted loop there around it. We can do the same. You know, we've got this dotted loop over here, which is self-containing things. So we can section these off and apply this same method each time. And this is what we're doing in some practice questions in a moment. The ladder one is a little bit different because we've got a much more extended object here where we're going to need to start looking at moments, how the ladder might be rotating, because the orientation, if this ladder starts slipping down the wall, it's going from being oriented that way as it slides down to eventually being flat. It's rotating the ladder. So we need to build in skills, which we'll look at a little bit later on in this series of videos, of how to deal with that rotation. But otherwise we'll still be using all of this. We'll still be doing our F equals ma, we'll still be doing our friction, we'll still be building all of this together. We'll just have a new set of equations as well that we'll be able to use to deal with this rotation. But all of our ways of drawing these force diagrams is applying the same thing over and over again. Weight straight down, reaction force perpendicular to every point of contact, friction opposing the motion, tension away from every point of contact if it's a string or a rope. If it's a fixed tow bar, you could potentially have the tension going the other way if we're pushing something using a tow bar, but that very rarely comes up. So that covers how we're drawing our force diagrams, and also showing with these sectioning off little bits of the diagram how they're really useful for directing our analysis and problem solving.